Good afternoon, all. Myself, Sagar Bhushan. Welcome you all to my RSA lecture series. Today, I am going to deliver a session on factor affecting the performance of vapor compression refrigeration system. So, the contents of this sessions are as follows. First, the introduction about VCR, that is vapor compression refrigeration, where I just give a short overview about its working principle and how this particular process is plotted on the pH chart. And thereafter, I will discuss about how the performance of this particular VCR cycle is calculated in the form of coefficient of performance. Then after understanding about its principle, then the coefficient of performance, then we will focus on our main topic, that is which are the factors that are affecting the performance of this particular system. So for that, I have considered four cases. The first is the effect of suction pressure, second, the effect of discharge pressure, third, the effect of superheating, and fourth is the effect of liquid subcooling. So, what is the effect of each individual parameter on the VCR system that we're going to study? So, let's start the discussion with understanding the principle of vapor compression cycle. So, vapor compression refrigeration cycle consists of four processes: compression, condensation, expansion, and evaporation. Okay. So here, if you observe this particular diagram, you can see that the low pressure and low temperature refrigerant is entering into this particular compressor from this particular port 1. And once it get entered into a compressor, the compression process takes place, due to which both the pressure and temperature of the particular refrigerant will increase to higher level. And after compression, the high pressure, the high temperature refrigerant will enter into the condenser where it get condenses and changes its phase from superheated vapor to the saturated liquid state. Okay, and during this phase change, the pressure will remain constant. However, there we may find certain drop in temperature. So after condensation, we get high pressure liquid refrigerant, and that liquid refrigerant will enter into this particular expansion mode where it get expanded to lower pressure and temperature. And during this expansion, there is also the phase changes take place, but not completely from liquid to vapor. It converts from liquid to mixture state. Okay, and that low pressure, low temperature mixture vapor will enter into the evaporator region where it will absorb the surrounding heat, and during this heat absorption, again, the refrigerant will changes the state from mixture state to the saturated vapor. And heat absorption, when takes place, then the cooling effect in that particular region get achieved. Okay. So after complete heat absorption, again that particular low pressure, low temperature refrigerant will return back to the compression process. So this is the cyclic process of vapor compression refrigeration system. So if you refer this particular TS diagram, here we can understand that 1 to 2 is a compression process where the saturated vapor is getting compressed to superheated vapor. And this entire compression process is in isentropic way, that is entropy remain constant. And after compression, the condensation taking place where we found that the superheated region is getting condensed to saturated liquid at constant pressure. And thereafter the expansion, where the expansion process is in isenthalpic way. So that is why here we can see the curved line instead of the straight vertical. And at the last, the evaporation process, where again the phase change is found to be observed from mixture state to the saturated vapor state. Okay, so this is the TS diagram. So for this particular ideal process, what will the performance? Okay, so for that, the parameter that we consider is the coefficient of performance, and it is defined as the ratio of desired output to the work input. So in refrigeration, the desired output that we want is the cooling effect. Okay, so that is why here we termed as an refrigeration effect, and the work input is in the form of compressor work. So the refrigerating effect is between 4 to 1. So that is why H1 minus H4. Compressor work is between 1 to 2. So H2 minus H1. And when we take the ratio of these two parameters, then we will get the COP of that particular system. Okay, so this is a short overview about this vapor compression refrigeration cycle. Now let's understand what is the effect of each individual parameter on the performance of VCR. So the first parameter that I consider is the effect of suction pressure. So this is the idle cycle of the VCR where the refrigerant which is entering the compressor in saturated condition and the refrigerant leaving the condenser is in saturated liquid. Okay. Now if we do changes in this particular idle cycle, then what will be the effect on the performance that we need to predict? Okay. So before that, let's understand what is suction pressure and what is discharge pressure. Okay. So this is the suction pressure, that is the lower pressure. This is the discharge pressure. Okay. Now, effect of suction pressure. It means that what will happen when we lower the suction pressure, that we need to understand. So when we lower the suction pressure to PS dash, so here what will happen? The parameter 4 will shift to 4 dash and here 1 will lower down. Okay. So this is the condition that we achieve. So by lowering the suction pressure, here we found that the net reflecting effect has been reduced. At the same time, the net compressor work has been increased. Okay. So for better understanding, I have added one more diagram. Okay. So if you observe here, this is the lower suction pressure. Okay. So due to the lowering the suction pressure, what has happened? This much amount of reflecting effect has been decreased. This much amount of reflecting effect has been decreased, and at the same time this much amount of compressor work has been increased. Okay, this much amount of compressor work has been increased. How? Because here by lowering the suction pressure, the point number one has shifted to lower side. Okay, point number one has shifted to the lower side. Due to this is the extra amount of compressor work has been consumed, and at the same time by lowering the suction pressure, this is the amount of refracting effect has been reduced. Okay, so that is a net effect by lowering the suction pressure. So here decrease in suction pressure results in decreasing in the refracting effect from H1 minus H4 to H1 minus H4 dash. Okay, H1 dash minus H4 dash. At the same time, at the same time, due to the decrease in the refracting effect, there is also a rise in the compressor work from H2 minus H1 to H2 dash minus H1 dash. Okay, so this is the net effect by lowering the suction pressure. Now, once we understand these are the effects, now let's identify what is effect on the performance. Okay, so as we know that the COP equation for any particular refrigeration system is net reflecting effect upon compressor work. So this is an ideal equation. Now when we apply our condition, that is lower suction pressure, what will happen? Here the equation will change. Okay, to H1 dash minus H4 dash divided by H2 dash minus H1 dash, where H1 dash minus H4 dash is found to be lower when we compare with this H1 minus H4, and at the same time H2 dash H1 dash is found to be higher when we compare with this H2 minus H1. So if you observe this particular section, okay, here you found that the numerator is getting decreasing and the same time the denominator is increasing. So what will be the final result? The final result will be the decrease, that is COP will decrease. So that is why under lower suction pressure condition, the performance is found to be lesser than the ideal condition of that particular system. Okay, so this is the net result that we get because of lowering the suction pressure. Okay, now let's understand the effect of second parameter, that is a discharge. So here again, this is the suction pressure, this is the discharge pressure. Now in the second case, what we do, we focus on the discharge. So here what will, now here we will understand what will happen when the discharge pressure increase to certain higher level. Okay, suppose I increase the discharge pressure to PD dash. What will happen then if I draw a straight horizontal line here? Okay, now this is the representation. So by lowering the discharge pressure, we can find that this is the amount of refracting effect has been decreased. Okay, and at the same time, this is the amount of compressor work has been increased. Okay, so for better understanding, I added one more diagram here. So this is the amount of reflecting effect has been decreased by increasing the discharge pressure, and at the same time, this is the amount of compressor work that has been extra consumed by increasing the discharge pressure. Okay, so this is the net effect. Okay, so by following this discharge pressure, then we found that the decrease in reflecting effect from H1 minus H4 to H1 minus H4 dash. Okay, at the same time, there is found to be increasing compressor work from H2 minus H1 to H2 dash minus H1. Okay, so again, here also we found that by low increasing the discharge pressure, the net reflecting effect has been reduced. At the same time, the compressor work has been increased. Okay, so when we put up this particular parameters in the COP equation, what we'll get? The equation will change to H1 minus H4 dash, which is found to be lower than the H1 minus H4, and compressor work has been changed to H2 dash minus H1 dash, again, which is found to be higher than the ideal H2 minus H1. So when numerator is getting decreased and denominator getting increased, then the final result will be the COP will decrease. So here also, when CO under high discharge condition, the COP value will be found to be lesser than the COP under ideal condition. Okay, so this is the net effect of lowering the discharge suction pressure and the discharge pressures. Now, even though we have come to know that by these two effects there will be decrease in performance, then also we apply such kind of or we try to achieve such kind of pressures because there is certain valid reason. So let's understand what is that particular reason. Okay, the first and foremost reason is the increase in discharge pressure is necessary for high condensing temperature. So wherever the high condensing temperature is required, in that particular case, it makes us to increase the discharge pressure to higher level. Okay, so when we increase the discharge pressure to higher level, then only the high condensing temperature can be achieved. This is the first and foremost reason. And the second is the decreasing suction pressure is necessary to maintain low temperature in the evaporator. It means wherever we require the ultra low temperature, in that particular case, the only option that we have is to lower its suction pressure. So when we lower the suction pressure, the temperature also get reduces. So whenever we need to attain the lower temperature or ultra low temperature, in that particular case, the suction pressure need to be decreased. And wherever we need to achieve the higher condensing temperature, in that particular case, the higher discharge pressure is must required. So that is why we try to apply these two effects on our VCR system for achieving our final output. Okay, so that is all about the effect of suction pressure and discharge pressure on the performance of this particular VCR. And in these both effects, the net COP will get decreased when we compare with the ideal condition. Okay, so that's all for this today's session. Thank you. Have a good day.